All right, this is video number 7 in the Crash Course to Chemistry series. Welcome back. I'm your host, Mr. Taylor. So let's talk about VSEPR. VSEPR is something that is on every single final, just to let you know. I know some topics I mentioned yesterday were more about just magnet or everybody. This one is an everybody problem. So VSEPR is the shape of molecules. And this is, of course, 3D shapes, okay? Atoms are able to use the three dimensions, and you can go from there. The best thing to do is to find the domain first. And the domain is literally how many things are connected to the center. And then 2, that will tell you the bond age. And while that is going on, I want to do some of this. Are we okay with Lewis structures? Should I go over Lewis structures? Thumbs up or thumbs down? Are we good on Lewis structures or bad?
What about the negative?
Sorry?
The ones here with the negative.
Are you talking about the, are you talking about like this?
Yeah.
So that would actually be polar or non-polar covalent. That's not something you need to worry about for this. Per se.
For this or
For the VSEPR things, that doesn't have anything to do with VSEPR. It has something to do with polar and non-polar covalent, and we can do that next if you want. Want to do that next? Cool, we can do that next. So next we'll talk about that. So I got, here's an example. Here's an example. Here's an example. And here's an example. Oh, that should have. You're on here. Okay, so these are 4 very different molecules. Again, I am assuming that you can do Lewis structures with balanced electrons going from there. So how many things are attached to the center of this? Show me the finger, show me the finger. 2, 2, 2, 2, 2, I saw 2 and I saw a few 4s. So with this, and that's a good thing for the 4, I know where you're getting the 4. It's 1, 2, 3, 4. You count the attachments. A double bond counts as one thing. So in this case, this one would be domain 2. This one has 1, 2, 3 bonds and an electron pair. So what's the domain of this? Okay, I'm seeing 4s. Again, this counts. 3 bonds, 1 electron pair. That is 4. This one is also 4. Uno, dos, tres, cuatro. And this one, 1, 2, 3. Yes.
we need to pass the graph into
So you're saying, that's an excellent point. So you're saying if you drew it more like a T-shape?
Yeah.
No. I can't speak for the other teachers, but I can tell you for me, I'm not marking points off on this. No, you get full points for the drawing. But I think you see, I'm drawing it like this way to kind of show what the bond angle is. I think you see that. I know you see that. But yes, this would be absolutely fine. Absolutely fine. And then here's where some of those things come in. Now I know some people use the magnet sets, some people use the Vesper modeling kits with little like sticks and balls and springs. Essentially, all the electrons want to get really far away from each other. Atoms, electrons specifically, don't like being next to each other. Negative things repel. You got negative and negative, they go away from each other. What's the furthest two things can get away from each other? It's a bond angle I know you're familiar with. 180. They are 180 degrees apart. That's the bond angle. The furthest three things can get away from each other would be what? And this drawing kind of shows it. Nice line. 120. And again, if you thought of the circle right, if you needed to nice and evenly get 3 parts to a circle, that's the 120, like a peace sign almost. That shows the 120, congruent angles. Here, you're far away as possible. This is where it gets weird. And I'm going to write this, especially on this one. The number one thing I have seen people mess up with the D4s is that they want to say 90. And it looks like 90. Can we agree on that? It looks like 90. But it's not 90. Neither is this one. Because I get people saying this one's 90 as well. When you have the third dimension, you actually have a little bit more leeway with the bond angles. Does anyone remember that weird number for this one? Close, that's the next one. 109.5. So when you have a tetrahedral shape, and I just grab the magnets really quick, because I know some students have seen these, and some have not. So a tetrahedral shape is going to look like this. So as you can see, as I spin it, it's definitely not a flat shape. It kind of looks like the Eiffel Tower a little bit, or the tripod stand that my camera's on. Maybe I should have brought that in the day I talked about it, because that clearly has it too. That's the 109.5. I think we can agree that's bigger than 90 degrees. So that's the shape that it's talking about. That's why it's not 90. People who are watching this video who are here, there's a chance one of you is going to say 90. I know that just because I've seen it happen so many times. Just make sure that's not you. It's easy to say 90, but it's not 90. And then those are domains 2, 3, and 4. All domain 4s are 109.5. It doesn't matter if it has an electron pair. If the domain is 4, it's 109.5. In terms of shapes, and if I am correct, and I might be wrong with this, the last time I remembered is that regular chemistry students, you are going to be given the table and you just have to use it to then figure out the shapes. Honors, I don't remember 100%. I believe you need to know this, and Megan, I can tell you for a fact you need to know this. For shapes, this one looks like a line, so we call that linear. Excellent. It looks like a line. This guy kind of has a triangle, but we know it's flat. So we'll call this one trigonal what? Not pyramid. It's flat. It's flat.
Trigonal planar.
Planar. Yeah, you were right the first time.
What's the difference?
Excellent. So what is the difference? And I'm actually going to do this one. I can show the difference. And can someone double check that this is in the shot what I'm about to show? So there is a difference, thank you. So a D3 a trigonal planar is going to look like this. I'm hoping this is in the shot. Should be. It's going to be flat, 120-degree bond angles. Nothing too scary there. Again, flat. Put on my palm. When you add the next one, you get the 109.5-degree bond angles again, but you also have an electron pair on top, which I'm showing with a different color, which is blue. This is a triangle-based pyramid. Because a pyramid is just a shape that goes to a point at the top. That's all a pyramid is. Any pyramid in geometry, it goes to a point at the top, but it has a triangular base. That's why it's trigonal pyramidal. And this is the 109.5. So this one has that added third dimension to it.
So I have four things. Not flat.
No, yep, if it has four things, it's automatically not flat. Correct.
So the triangle is what I can
Correct. Unless, for example, that CH4, that methane, what's the shape for that one? Does anybody remember the shape for that other one? I know it's not up yet. The CH4? That one's not triangular pyramidal. That one's a totally different shape. Tetrahedral. Okay. Again, if you needed to, you can just rewind the video, go back to that part. But essentially the key thing is the triangle pyramid one has that added height to it. That's the D4. Again, 1, 2, 3, 4. The planar one is flat as a pancake. Again, I know you probably can't see that well, but it does fit flat on the palm of my hand. Tetrahedrals, the Eiffel Tower kind of shape, are going to look like this. Again, 4 bonds. I know you guys are pretty familiar with tetra meaning 4 because of the covalent naming. Tetrahedral is a 4-sided bonded shape. And those are really the main shapes. Like those are the most popular ones. These 4 right here. Please keep in mind these bond angles are the same. I get a lot of people sometimes try to switch them up a little bit. You don't need to do that.
How is the tetrahedral one different than trigonal? Like
This one?
with the model.
With this one with the model?
Yeah.
Okay. So that one, the reason why it is pyramid, again, it's kind of, that's the part I was actually just going over. If you have D4, and I think we can agree this is D4, and it's 4 connections, right? Triangle, do you see it? And it goes to a pyramid, that's a pyramid. So it goes to a point, so trigonal pyramid. That's where I'm getting that one. This one's the flat one.
No,
Oh.
between that one and tetrahedral.
Oh, I'm sorry, okay. So the difference between that one and tetrahedral, excellent. So, do you know where electrons are? No, they're too small and too fast. Do any of you know where electrons are? Do I know where an electron is in an atom? Do any of your teachers know? No. We have really good guesses. That's the electron configuration, the orbital diagrams, all that stuff. A tetrahedral shape is when you have 4 distinct bonds that you can clearly tell with the shape. So that one's going to look more like this. If you have the electron pair, it's like it's not even there for the shape. It's invisible, right? You don't know where the electrons are. It's there, and that messes with the bond angles, but it's not there in terms of the shape.
Which one is
This one's a trigonal pyramid. So this is a domain 4, 3 bonds, 1 electron pair. But again, electrons, you don't know where they are, so they don't count for the shape. It's like you cover them up. The tetrahedral one is a 4th bond. That you count. That's going to look like this.
So that electron figure that's on every diagram,
Yes.
it's gonna count as a domain.
It is a domain, yeah. Electron pairs are a domain. Electron pairs are one domain, a single bond is one domain, a double bond is one domain, a triple bond is one domain. So you count all those as one equal thing. So again, I've seen people do this, not really with, again, from you guys, to be honest, with the group that's sitting here, but some of your classmates have done this. And they just count the circles. Some of your classmates do that, and that's how they get the domains. So they don't care about the double bond, they just circle what's on the outside.
But would that work every time?
It would work every time, but some people I've seen try it, but then they like, I've seen this. I've seen people do this and then count it as 4. I know what they're doing. Again, I don't blame people for saying 4 on this, but the nice thing about that example, and I'm actually going to erase some of this. If you draw this right, none of you draw carbon dioxide like this, right? None of you do that. Do any of you draw like that? No. And no one, like, I see it once a year maybe, total. You guys draw this one nice and linear because it's linear. It works out really well. So don't overthink this one. This one's flat, it's a line, you're good.
So how can you tell like if one has to be linear?
Excellent. So this one, there are 2 bets. And then I'm going to mention the one you were talking about. So with bents, you might have something like water. Or you could have something like CH2. Now CH2 is a little weird. I know some people have done it, some people haven't. You saw it on a homework, or saw it on a test. This is domain 3. This is domain 4. 1, 2, 3, 4. 1, 2, 3. And these are both bent. Bond angle, this is D3, so the bond angle stays in 120. And this one is D4, so the bond angle stays at 109.5. And what happens here? Again, electron pairs don't count in the overall shape. So what occurs let me show it like this. Let me draw it. So this is water. Water has that domain 4 look to it. It kind of looks like a tripod still. But do you care about the blue electron pairs really? No, they're there, but they're not there for the shape. I think we agree that's bent. 109.5. No big deal. With the other one, if you have domain 3, it's going to look like this. Again, electron pairs don't count. This one's probably a little easier to see. That's bent. Okay, chemists are lazy. They came up with this non-linear name for bent, and you can kind of go from there. And that's how you can tell. So essentially, if it's got an electron pair, it cannot be linear for the sake of this class.
Do you have any domain that can still be bent?
I might have misheard you because of that. The only 2 bents would be domain 4 and domain 3. Domain 2 does not have a bent. Domain 5 doesn't either, and domain 6 doesn't. The only ones would be these 2. It is fair game. Well, water is one of the most famous molecules, right? You know you're going to see probably something with water. Are you going to see this part? I don't know, but you're going to see something with water.
But like,
Oh, sure. Oh, yeah, it'd be fair game. You guys did it on a test, you did it on the homework. You guys are actually really good at this. This is just a refresher. You guys were very good at this, but you can get good again. Yeah. Yep. Yeah, so a bond is one domain. Even if it's a double bond, it's still one connection to this. I know it's weird to kind of say, but a bond is still one thing. A double bond is a bond. That'll be domain. You guys only count the things on the center. So there's no electron pairs on the center, you're good to go. That's actually a really good question. So I know off camera you didn't hear that. The question was, would you count these in the domain for CO2? And the answer is you wouldn't have to. It's only how many items are on the center. Because carbon is the center, and I don't see any dots, you're good to go. So these would not count for this. These would not count for this either. It's literally just the connections. And then the last two to do. And then the other two to talk about really quickly. I know some of your teachers might have shown you the three-dimensional way of drawing it. I am not going to do that right now. What haven't I done on the F's yet? Do you have to do the electron pairs? Yes, why? Why do I have to show all these dots? There's a specific rule that you have to show. Octopus, octagon, octet rule. You gotta show the octet rule, right? Things want 8 electrons to be stable. The dots show the 8. These guys are your only other shapes. Domain 5, domain 6. This will be 90 degrees and 120 degrees. These are the 90s, these are the 120s. And then these are only 90. Shape names. Trigonal Bi-Pyramidal and octahedral. So, what'll end up happening is this. If you have a domain 6, it's going to look like this. Those are your 6 connections. And you can see that there are, I know it's not perfect, but those are 90-degree angles. There, 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 there. And if I flip it, they're all still there. So that's the octahedral D6. And then trigonal bipyramidal is a trigonal planar with a linear stuck right through the middle, like this. Try to show this like that. Again, I'm holding on the one on the back. 120s. I know it's not perfect, but those are the 120s. And then the 90s are here, the bottom one, that one, and you can kind of see. I know it's kind of falling apart a little bit, but those are the 90s. And that's really Vesper.